Derive is my first 13.6 kilogram combat robot, initially built to compete in the Australian full combat class, and was rebuilt to Sportsman spec, where the high energy spinning weapons are prohibited. It's a fairly competitive machine that has been documented well in previous videos, but this next event might be the toughest one yet. I'll be making the trek overseas from Australia to the Robot Rampage Grand Opening Tournament in Auckland, New Zealand, which is a full combat event. Only catch is that I finally committed to going to the event about 9 days out, with the only robot available not ready to handle big spinners. Let's see what can be done to give my machine a chance at surviving the event. Derive S is the aforementioned Sportsman flavour of this frame I built way back at the start of the year. Said frame is more or less the same as the original robot, with certain changes being made around it, such as ditching the spinning disc to upgrade the lifter to a grabber, but crucial are the larger drive motors than originally fitted, which is the first element to rear its head. Ideally, I'd simply revert the robot to the full combat configuration, as the spinner parts are still on hand. Unfortunately, there are two major problems with that. Firstly, the spinner uprights and surrounding components failed in combat. The design was simply not strong enough. Now, I could just remachine the old parts again, but actually fixing these problems requires a redesign of the frame, which is simply not on the cards. Secondly are those larger drive motors. The original Derive had 50-45s for traction, but these lacked torque and got quite hot by the end of the fight. For the later Sportsman event, these were replaced with 50-65s. They definitely improve performance but are 20mm longer. This length eats up the space that used to allow battery wires to pass around the spinner motor and connect to the motor controllers. It's really not that practical to either revert to the older motors or find some janky workaround for the wires, so the spinner module is simply off the table with the time on hand. So we're stuck with the configuration of Derive S. The grabber is neat, but will likely fail if it bites down on a spinning weapon, which is our first problem to fix. Previously, the spinner acted as very effective spinning armor, but without it, something needs to fill that void. Finally is an electrical problem that meant the robot could only drive forward effectively, but there'll be more on that later. Firstly are changes to the jaw. While quite pretty, the 3 pieces of aluminium construction is heavy and too strong for its own good. If you don't design in a point of failure, the universe will pick one for you, and chances are you won't like where it is. With the old mechanism, I'd bet the weakest link in the chain is the gearbox or the chain itself, as the long and very tough jaw would amplify a spinner hit. What would be nice is if the jaw itself would bend away during hits like the current side armor. Thinning out and redesigning the jaw to be made of HDPE plastic saved 800 grams on the spot, as well as being a more durable system. It will be munged to no end by the end of the event, but I'd rather lose $15 of plastic than a $150 gearbox and a fight. The gear remained aluminium to retain its strength for the lift, leaving a removable plastic element for the future. Without the spinner in the center of the robot, I've added a piece of 6mm steel bolted to the middle frame block. This piece of aluminium is on the shortlist to be the most crucial structural element in the entire robot, the keystone to this aluminium arch. All lengthway frame rails and fork mounts are held together by 4 8mm bolts that thread into this block, and without them, the front end more or less collapses. Bonus points, as the lifter does its work, this block keeps the front of the robot from folding into the floor. You might be wondering where this piece was in the old design where the spinner was present, but there the entire spinner assembly took place of this block. I'd like to highlight again that design failed, which led to the chassis warping badly. With the plastic jaw on the Sportsman configuration, the robot was approximately 2 kilograms underweight of the 13.6 kilogram limit. It felt appropriate to make large, durable forks to rely on during engagements. They stick out farther than the lifter, so it protect it from drum spinners and lift opponents higher off the ground to ensure they can't escape of their own accord. It was decided that these would be one of the major upgrades to the robot, besides the plastic jaw. To save time, there are only 3 unique parts to the fork assemblies: a side fork, a front deflector, and a stiffener plate. These could be welded together with the TIG machine conveniently placed next to the plasma cutter at work. A minor problem to fix before making the new parts is the lifter gearbox bushing. In both previous events, the exposed end of the lifter gearbox was supported by a printed bushing riding in an aluminium hole. It kept the gearbox from pivoting in its mounts, which is a problem discovered all the way back in the first test lifts. Surprising no one, these PLA bushings never handled the forces well, and probably didn't do much at all. Come to think of it, it's probably the cause of the inconsistent lifting performance at the last event. A ball bearing was finally procured to support the shaft properly. With a spare afternoon, I procured the laser cutter at work to make the fork parts. These are very interesting and often cost-effective machines. Fundamentally, this one is made of an off-the-shelf handheld plasma torch mounted to a 3-axis gantry. It's controlled with Mark III like many older CNC contraptions, but with a twist. The height of the torch and workpiece is very important to get right, as if the distance becomes too great, the arc will collapse and lead to a failed cut, or too close and simply collide the torch into the workpiece. This is compounded by the fact that the metal is just laid on top of the warped machine bed and thus anything but flat. That's where the torch height controller comes in. Its job is to finally control the Z height of the torch. It monitors the voltage across the torch. As the gap increases or decreases, the voltage will change, and thus a simple control loop is implemented to nudge the torch up and down. One has to tell it the thickness of the material and some other properties so it knows what to listen for, but it's not much more complicated than that. It also handles enabling and disabling the torch with a relay rigged into the handheld unit. 2D vector files are brought into the CAM software to generate G-code. This machine needs offsets depending on whether it's an internal or external contour to ensure you get the part you want. If the torch simply followed the part outline, you'd have something with all contours offset by the thickness of the plasma's path. Similarly, the torch needs space to strike an arc off of the side of the desired path, which is known as lead-in. This striking is often messy and gets performed a few millimeters away before leading in. Be careful that this lead-in does not cross into the other part. With G-code generated, the sheet metal is placed on the bed and held down by the weight of a large metal cube. A clamp attaches the workpiece to provide an electrical path to ground for the plasma torch. Due to the fumes and the light generated, the entire machine is enclosed in a tent made of welding tarp. During the cutting process, one has to keep an eye out for parts that don't fall all the way out. If they get stuck in the path of the torch, it will cause the machine to crash.
You have to make sure as well, when the parts drop out, they don't get tip up.
One can see in this footage the torch height controller in action. What exactly this readout is displaying, I'm not so sure, but it's somewhat stable during cuts and dips when the torch travels. I presume the control loop is intending to keep this value consistent while blasting away material. After cutting, the corner of the tent is cracked open and the machine left alone for a while to vent all the fumes. Once clear, the parts are removed and all flashing is ground off. These parts need to be welded, so all contaminants should be removed now. These parts will be bonded using the TIG welding process. I have a little experience with this, but got help from Glenn on the specifics for hardox. Apparently one needs to use stainless steel filler rod to avoid hydrogen embrittlement. Crank up the current quite high and move pretty quickly. To hold the parts in place, one can use a combination of pins and magnets on a welding table, but practically some G-clamps on a bench at home would do the job as well. When I lay down these welds, the parts will move as the molten material contracts, and there's no way around that without involving some pretty hefty jigs. Firstly, the stiffener plates are tack welded in place. This is the practice of placing small point beads that can be easily broken off if it turns out there's a problem before final welding. Being my first time welding hardox, so far so good. Next is to tack in place the front defector plates. Some scrap material spaces the forks up to let me grind in the front plate to a tip later on. These tack welds look strong, but we can see some erosion where I let the part get too hot. Positioning looks good enough, time to lay down the proper welds. These first two are pretty disastrous, with lots of erosion and ugly inconsistent filler. It's because I held the welding torch too far away from the part when welding. The arc leaves the tip in a cone shape. The farther away it's held, the wider the affected area when it hits the part. Therefore, it takes longer to superheat the required area to melt metal, all while dumping heaps of undesirable energy into the surrounding material. During these welds, the torch got so hot, it partially melted and warped the copper inside that holds the tungsten. Thankfully, these are cheap and easy to replace, almost as if they were prepared for novice mistakes like these. Learning from this, the next welds look quite a bit better. This one in particular, a fairly consistent bead that isn't discolored without eroding the surrounding material. Finally are the welds on the deflection plates. Not great, but not terrible. Still holding the torch too far away on these ones. To note, the reason one may bias to keeping the torch at distance is that if one accidentally touches the torch to the part, it will short out. With this, the arc collapses and you typically have to regrind the tungsten tip, as it will be damaged by the interaction. I'm kind of doing the same job as the plasma THC when you think about it. With that, the parts are complete. I made sure to weld the stiffener plates from underneath so that no one will ever see the poor welds. When designing parts for plasma cutting and welding, it's worth keeping in mind the limitations of the technology. This plasma cutter is accurate to maybe 1mm if you get lucky, and welding will warp the part even further. As such, I left 2mm of space between the forks and mounting blocks, and specified a 12mm hole for a 10mm bolt, knowing that the hole would be oval-shaped. Having made good time, we've got a pair of pretty substantial looking forks. Time will tell if they hold up. While the plasma cutter is working, I got Glenn's help to fix the drivetrain motor problems from the last event. For whatever reason, the drive motors would only turn to full speed in one direction, failing to commutate when spinning the other. Extra puzzling was that the problem flipped direction when the motor was flipped in firmware. This was only present with BLDC mode. FOC seemed fine but drove poorly. We arrived at the solution of switching the controller from censored control to hybrid control. But what does this actually mean? To commutate a brushless motor, we need to know where the rotor magnets are in relation to the stator coils at all times. This is done with 3 Hall sensors placed at specific locations around the motor. Listening to these and pulsing the phases in sequence is called censored control. This is very reliable, but requires those sensors to be present, often a fragile assembly and too large for small motors. Drones use a different system imaginatively named as sensorless control. As rotor magnets sweep past the coils, they induce a current. The motor controller can listen for this and deduce the position of the rotor. The problem with this method is that the rotor has to be moving at speed over the coils to pick anything up, meaning starting is a rough manual process. To cut a long story short, censored control is excellent at starting a motor and running at low speed, but can begin to fail at high ERPMs. This is due to a combination of inaccurate sensor positioning and hysteresis in the units themselves. Sensorless is a very inefficient and rough way to start a motor, but once it's running, this method is far more accurate and reliable at high speed. Back to the VESC motor controller, this unit is capable of starting the motor in censored mode and then switch to sensorless commutation once the target ERPM has been reached. Note that this is the electrical RPM, not the motor RPM, as the electronics only care about the rate at which the phases alternate. While this motor is a very slow turning motor, it is a very large number of poles, and is operating at a high voltage, meaning the ERPM is high despite the RPM being low. Therefore, the motor controller can use the best of 2 technologies to get the best motor performance. For my drivetrain problems, this fixed the reversing instantly. It appears the VESC can't keep commutation going with Hall sensors at high speed. It's a pretty wondrous piece of tech to not only be able to implement both control modes, but smoothly switch between them at such high speed it doesn't miss an electrical beat. Okay, so read, we want to go to hybrid. Right. So it should have data, so Holding it. Sweet. That work?
Sounded good. It has a little stutter. But I noticed
It looks better on the bench. Hybrid.
Yeah.
We didn't actually fix the problem, we just patched it by having sensorless on top of the censored, which is good enough for me. Cool.
Yeah.
Put it
Well,
back together.
that's pretty standard.
Yep. Still good.
Oh yeah. That's definitely it.
The last parts to make are a few components in the HDPE jaw assembly. These are all made the usual way by cutting a slot profile out of whatever cheap stock material I can get my hands on. Before putting the robots together, I want to highlight a particular detail about how the CNC machine drills holes. It doesn't simply plunge the drill in, but performs a pecking motion, drilling about 1 millimeter at a time and then retracting the tool. From this slow motion we can see why. As the mill can drill very consistently, the tool forms a long continuous chip. If one programmed the machine to simply go in one pass, it would have a very long and potentially hazardous string of aluminium swinging around. By retracting occasionally, it breaks the chip at a reasonable length and lets it free before repeating. I try to do this when drilling things by hand as well, when encountering the same phenomenon. With the pieces made, this robot is thrown together. When pulling the old jaw off the robot, I noticed the shoulders on the shaft had been mashed in and gained a bit of crowning, but that was fixed with a file. The middle armor panel is bolted on with 10mm bolts, and the jaw is tied together with a couple of 6mm bolts. These normally wouldn't hold up to the forces, but if we're relying on the HDPE to limit the energy, it should be okay, but time will tell. With these changes, we have an assembled robot ready to put on the ground and test. Looking good, it's mechanically ready for New Zealand. I've still got all the forks and jaw if necessary, including the old lifter arm and the top jaw. The robot weighed in at 12.7 kilograms, meaning I've got 900 grams to play with. I'm not sure what I can actually do with that weight in the 4 days I've got left before the event, but nonetheless it's probably time to get packing and ready to go. It should be a pretty good time. There's another Australian team going, meaning 2 of us trying to put the Kiwis in their place. We'll make a video with an event report next. Until next time.